Welcome to the Deep Dive. You asked for the quick version on how the universe began, so today we're hitting the Big Bang Theory.
And also touching on some of the, let's say, stranger ideas, parallel universes, extra dimensions, that kind of thing.
Exactly. Your shortcut to cosmic origins. Let's jump right in.
Okay, so the Big Bang, it wasn't just like one person's sudden idea. It actually built up over time, starting maybe early 20th century.
Right, people like Georges Lemaitre, I think he had this primeval atom concept back in 31.
He did, yeah. A tiny, dense beginning. And around the same time, actually a bit earlier, Alexander Friedman was working out the math based on Einstein's relativity.
Showing the universe could expand, which was pretty radical then, wasn't it? Most people thought things were static.
Absolutely. A lot of astronomers were, well, skeptical. It needed evidence.
Which brings us to Hubble, Edwin Hubble, in the 1920s.
Yeah, his observations were crucial, seeing that galaxies weren't just sitting there.
They were moving away. And the further away, the faster they receded. Redshift.
That's Hubble's law. It strongly suggested everything was closer together in the past. An expanding universe implies, well, a smaller beginning.
And the name Big Bang, I heard it was meant as an insult.
Yeah, sort of. Fred Hoyle coined it on the radio in '49. He wasn't a fan. He preferred the steady state idea.
Funny how that stuck. So, okay, the theory developed more in the 40s.
Right. George Gamow and his team, they fleshed it out and made a key prediction.
The CMB, cosmic microwave background.
Exactly. They figured if the universe started super hot and dense, there should be some leftover heat, some afterglow radiation permeating everything.
And then, almost by accident, Penzias and Wilson found it in '64.
Yep, this faint cold microwave signal, about 2.7 Kelvin, it was everywhere they pointed their antenna.
That must have been a huge moment, like finding the echo of creation.
It really was. It pretty much sealed the deal for the Big Bang over steady state. And later missions, CHOBE, WMAP, Planck, they mapped it in incredible...
Showing tiny temperature variations, the seeds of galaxies and stuff.
Precise. Those tiny fluctuations were the starting points for all the large-scale structures today.
So the core ideas are expansion, a finite age, was it 13.8 billion years?
Roughly, yes, based on expansion measurements and the CMB data.
And this initial state, incredibly hot, incredibly dense, a singularity.
Well, that's the term, though, our physics breaks down there. Before that, maybe all forces were unified. It gets weird really fast.
Okay, let's walk through that early timeline after the absolute start. Planck epoch, then inflation.
Yeah, the Planck epoch is that first tiny fraction of a second where we really don't know the physics. Then comes inflation, around 1036 seconds.
Which was this period of insanely rapid expansion.
Exponential expansion. It blew the universe up huge, smoothed it out, explaining why it looks so flat and uniform on large scales. A really crucial step.
Then what? Electroweak era.
Right, forces start separating. Strong force breaks off. Then you get the quark era, super hot quark-gluon plasma.
Okay, quarks, electrons, neutrinos. The fundamental building blocks are there.
Then things cool a bit. Quarks bind into protons and neutrons. That's the hadron era. Lots of matter-antimatter annihilation happening.
Leaving just a tiny bit of matter left over, which is up.
Then the lepton era, dominated by electrons and similar particles. And crucially, nucleosynthesis begins.
Making the first light elements, like hydrogen and helium.
Yep, for the first few minutes. Then the photon era dominates for a long time. The universe is still too hot and dense for neutral atoms. It's opaque.
Until about 380,000 years in, recombination.
That's the magic moment. Electrons finally combine with nuclei to form neutral atoms. Suddenly, photons can travel freely without scattering.
And that's the CMB light we see today, released way back then.
That's it. The universe becomes transparent, but then it enters the dark ages.
Dark age. Sounds ominous.
Well, transparent but dark because no stars had formed yet. Just gas, slowly clumping together due to gravity acting on those initial density fluctuations.
Until gravity won and the first stars ignited, maybe 400 million years later.
Something like that, yeah. Ending the darkness and starting the era of stars and galaxies.
So pulling back, the Big Bang Theory just explains so much, doesn't it? The expansion, the CMB, the element abundances.
It's incredibly successful in tying all those major observations together. No other model comes close, really.
We mentioned alternatives like steady state or tired light briefly. They just don't fit the data, especially the CMB.
Right. They have significant observational problems. The Big Bang remains the standard model because it works so well.
But the big question remains, what was before the Big Bang? Or is that even a valid question?
It's the edge of our understanding, maybe beyond it. The theory describes the universe from that initial hot, dense state onward. Asking before might be like asking what's north of the North Pole.
Okay, but people speculate, right? Eternal inflation, cyclic universes.
Oh, definitely. Eternal inflation suggests our Big Bang might be just one bubble forming in a larger, eternally inflating multiverse. Cyclic models propose bounces, contractions leading to expansions, quantum fluctuation ideas.
So maybe nothing isn't quite nothing in quantum terms.
Possibly. But again, this is highly theoretical, no proof.
Which leads us nicely into parallel universe. This multiverse idea seems popular.
It pops up in a few contexts. Quantum mechanics, the many worlds interpretation, suggests reality branches with every quantum event.
Creating infinite parallel worlds.
Wow. And cosmic inflation, as I mentioned, could naturally produce countless bubble universes, potentially with different physical laws.
Could our universe not even be the first one?
In some of these scenarios, sure, but again, zero direct evidence. It's fascinating, but speculative.
Okay, and lastly, higher dimension, string theory, M theory. They talk about, what, 11 dimensions?
Yeah, our standard model is 4 dimensions, 3 space, 1 time. But theories trying to unify gravity with other forces, like string theory or its extension M theory, often require extra spatial dimensions to work mathematically.
M theory needs 11, 10 of space, 1 of time.
That's the framework, yes. People like Edward Witten were key in developing that. Even earlier, Kaluza and Klein tried adding a 5th dimension back in the 1920s.
But where are these extra dimensions? Why don't we see them?
The idea is they're compactified, curled up incredibly small, like Planck length small, far too tiny for us to perceive or interact with directly.
So they're a mathematical necessity for the theory, but hidden from view?
Essentially, yes. It's a way to make the math unify the forces elegantly. Still very much an area of active research, trying to find ways to test these ideas.
So wrapping up, the Big Bang provides this really solid story for our universe's evolution, backed by hard evidence like the expansion in the CMB.
Absolutely. It's the bedrock of modern cosmology.
But there are these huge remaining questions. What happened right at the start or before? Are there other universe, hidden dimensions?
And those questions are what keep cosmology exciting. They push us to develop new theories, new experiments.
It really makes you think, doesn't it? If inflation theory is right and we're just one bubble universe, imagine what else could be out there. Different physics, different realities entirely.
It's a mind-bending possibility, a universe of possibilities, perhaps literally.
A perfect thought to ponder. Thanks for joining us for this deep dive into the cosmos.